We've discussed previously that the product of two vectors is not defined. It does not make sense to multiply two vectors. But now we're going to talk about something known as the dot product, which is a product in a certain sense. Frequently in the context of vectors, especially in physics, one wants to know how much of one vector points in the same direction as another vector. And the dot product allows us to compute this quantity. So here's a simple example in the context of work and force. Suppose we have a force of constant magnitude F, and it's applied to move an object from a point P to a point Q. The work required is the product of the force and the length of the segment connecting these 2 points. If PQ denotes the displacement vector from P to Q, then the work is just the force, the magnitude of the force, times the length of displacement vector PQ. So keep in mind again that I talked about F as being the magnitude of the force, so it's really the magnitude of the force vector. Notice that that's an arrow there. And the length of PQ is nothing more than the length of the displacement vector from P to Q. So you may have seen in integral calculus or elsewhere that work is force times distance. So here's our force, and here's our distance, which is nothing more than the length of the vector starting at P and ending at Q. Well, let's suppose we have something that's a little bit more complicated. Suppose F is a force vector having constant magnitude, I've expressed that, whose direction is not the same as PQ, but which makes an angle theta relative to the displacement vector from P to Q. So we have a picture that looks like this. Here's the displacement vector from P to Q. Here's our force vector, and I've drawn a little right triangle. What I want to do is I want to compute or determine how much of that force is pointed in the direction of our motion. In other words, we want to compute this distance, this length, because that length times the entire length is going to give us the work done. In this case, because the force is not pointing in the same direction as the motion, we actually need to compute this component. Well, we know that the magnitude of this vector, the length of this vector, is just the magnitude of F, which I've denoted there. We know that the cosine of this angle theta is the adjacent, which is that length, divided by the hypotenuse, whose length is right there. So if you use a little bit of trigonometry, just rearrange things, this distance right here would be the magnitude of F times the cosine of theta. So the work done, if this is our force vector, and we are moving something from P to Q, the work done would be this product right here, the magnitude of F times the magnitude of PQ times the cosine of theta. So I've taken this distance, which is PQ, I've taken this product, magnitude of F times cosine of theta, and I've just rearranged terms a little bit. We call the quantity magnitude of F times the magnitude of the displacement vector PQ times the cosine of theta. It's the dot product of the two vectors F and PQ. More generally, if U and V are vectors, then the dot product is defined as the magnitude of U times the magnitude of V times the cosine of theta, where theta is the angle between U and V. And we write this way. So we say U, and then we put a bullet or a large dot between V. It's the magnitude of U times the magnitude of V times the cosine of theta. So here are some important things to realize. This is a scalar, that's a scalar. The cosine of theta is a scalar. So the dot product of vectors U and V is a scalar. It only makes sense to start with two vectors and then compute their dot product, which is a scalar. So this is why the big dot is important. There's a difference between 3 dot U and 3 times U. 3 times U simply means take the vector U and stretch it by a factor of 3. 3 dot U, using the dot product symbol, makes no sense, because in order to take the dot product of two quantities, both quantities must be vectors, and 3 is not a vector, it is a scalar. Take a look at a simple example. Suppose a constant force of magnitude 5 newtons is applied to move an object from the point P equals 1, 2 to the point Q equals 9, 8. If the angle between the force vector and the displacement PQ is 30 degrees, how much work is done? Okay, so let's find the displacement vector from P to Q. We subtract the coordinates of P from the coordinates of Q. 9 minus 1, 8 minus 2, that gives me the vector 8, 6. So that is the vector PQ. The work would be the dot product, which is the magnitude of F times the magnitude of PQ times the cosine of 30. Now the magnitude of F was 5, and if we compute the length of the vector 8, 6, 8 squared plus 6 squared gives me 100. So I'd have the square root of 100, which is 10. 5 times 10, and the cosine of 30 degrees is root 3 over 2, so all of this simplifies to be 25 times the square root of 3. Now you'll notice in this case, to compute the dot product, we actually had to know the angle between the two vectors, and typically that's not the case if we have the vectors in component form. So suppose we have two vectors in component form. These are going to be vectors in R3, 1, 2, 2, and 0, 3, 4. We don't know the angle between these two vectors. We can calculate their magnitudes, but we can't calculate the angle between them. It ends up that one can use trigonometry to come up with a different formula for the dot product, which is very convenient when we have the vectors in component form. Really, it comes down to the following. Multiply the corresponding components together and add them. Try to focus that again. Okay, so take 1 times 0, which is 0, plus 2 times 3, which is 6, plus 2 times 4, which is 8. So we multiply the corresponding components and we add them together, and we get 0 plus 6 plus 8, which is 14. That's a much easier formula to use, but it requires that we have the vectors in component form. But now that we have the dot product, we can actually figure out the angle between these two vectors by combining the two formulas. We know that the dot product on the one hand is 14 because we computed it using this formula for the dot product. On the other hand, the other formula for the dot product says that the dot product is the magnitude of u times the magnitude of v times the cosine of theta. Well, if we know what u and v are, we can calculate their lengths. So this is the length of u using the distance formula, the length of v using the distance formula. The length of u is 3, the length of v is 5, so we know that the dot product above 14 has to equal 3 times 5 times the cosine of theta. If we solve that for cosine of theta, we get 14/15, and the arc cosine of that is about 0.37 radians. So to summarize, if you have two vectors in component form, there's an easy formula to use that involves multiplying like components and adding. And once you know that, you can actually use the other formula for the dot product to find the angle between the two vectors. The dot product has some nice properties. For example, the dot product is commutative. If we take the dot product of u and v, it's the same as the dot product of v and u. If the dot product of two vectors is 0, that means the cosine of the angle between them is 0, which means the vectors form a 90-degree angle. So they have to be perpendicular, or the word we also use is orthogonal. The dot product distributes across addition. The dot product of u with the sum v plus w is u dot v plus u dot w. Notice how these are going to both be scalars, so if we add them together, we get a scalar. Now here's a really useful property. Suppose we take a vector u and we stretch it by some scalar a, and then we take the dot product of that with the vector v. Well, we can take the scalar out, a, and it's nothing more than the dot product of u with v times a. Similarly, if we stretch v by a factor of b, then take the dot product with u, we can just factor that constant b out. And this is sometimes referred to as bilinearity. So taking a look at a couple examples, suppose we look at the vectors 4, 6, 0, and 3, negative 2, 1. If I want to compute the dot product of these two vectors, because I have them in component form, multiply the corresponding components, 4 times 3, plus 6 times negative 2, plus 0 times 1, I get 0. So that tells me that these two vectors are perpendicular. They form a right angle. Let's go back to the vectors on the previous page, 1, 2, 2, and 0, 3, 4. We saw there that the dot product of u and v was equal to 14. So what would the dot product of 2u and v be? Well, the bilinearity property says that we can factor this 2 out, and we'd have nothing more than 2 times the dot product of u and v, 2 times 14, which is 28. Let's say we wanted to compute the dot product of 2u with 3v. We could factor the 2 out, we could factor the 3 out, so we'd have 2 times 3 times the dot product of u and v, 6 times 14, which is 84. Here are some problems I'd like for you to work on in preparation for class. Suppose I've given you this vector u and this vector v. Compute each of these quantities, as well as the angle theta between the vectors u and v.